There's something between interesting. So what we studied was a reactive algorithm which says that my current linear speed and my current angular speed is a function of nearest obstacles with their speeds and directions and angle to goal and distance to goal. We did not use distance to goal here. Now, in the previous courses, we have studied something like the A star algorithm, which was more or less deliberative algorithm. If I do this, then this happens, then this happens, and this happens, what happens? So you go from the source, you apply all possible velocity, you apply all possible actions. From this, you apply all actions, you apply all actions. It's prioritized, so you can change the priorities of processing of nodes, and eventually you reach to a goal, and this becomes your path. So that's an optimal search. Now, in potential field and in velocity obstacle, it would be inquisitive to know why am I not applying A star algorithm. It's a standard case of A star algorithm. And the reason why for this problem I'm not applying the A star algorithm is because the A star like algorithm, they only work on discrete spaces. Now, a graph has two parts, vertices and edges. And there are two types of A star algorithm, as a graph search and as a tree search. In a graph search, if I come to a state, if I revisit a state, if I go back to a state, I say I've already been here. I prune it. And in tree search, even if I go to a state again, I do not prove it up. So instead of the A star algorithm, let me call it as a general graph search. Oops, then there'll be a confusion. So let's say A star algorithm. It operates either as a graph search or as a tree search. In a graph search, repeated states are pruned. In a tree search, repeated states are not pruned. And of course, there is a famous cartoon by which we show it. So that's a graph search. Non-prioritized. And here what happens, this was the state A, and this produces the same A. So instead of this, I say this has already been produced and I prune it up. I don't expand it up. Tree search, we show it by exactly the same cartoon. So it's A. I will still continue. It's a pruned. Now, the reason this is because of the assumption. Here my assumption is the states are discrete and my actions are discrete. So this is 1, 2, 3, 4, only 4 edges because there are 4 discrete actions. My actions are discrete. States are discrete so that this A and this A can be mapped. If A wouldn't have been discrete, 2 real numbers can never be checked for equality. So my assumption in a tree search is that number one, the actions are discrete. And take it very clearly that states may not be discrete. And that's why in a graph search, in A-star-like algorithm, we always say that the actions need to be discrete. States, I don't care. If they are discrete, I have the liberty of a graph search. If not, tree search is good enough. Complexity turns out to be exactly the same we've learnt in the previous courses. So A-star algorithm as an optimal search can be applied whenever your actions are discrete state do not matter. Now, why did I use potential field? Why a potential field? Why velocity obstacle? Why not a A-star-like graph search algorithm? The number one reason was that it's discrete. Of course, there is a number two reason, which is to deal with the complexity as well. Reactive algorithms are fast. Graph search algorithms are the ones which are taking a long time to compute. That was the other reason. So, in that also I can say that why do I need to plan from source to goal? I just need to plan from source, let's say for 5 seconds, for 10 seconds, then maybe A-star algorithm is not computationally infeasible. So my only problem is that in A-star algorithm, the actions need to be discrete. Now there's a limit, there's a problem that we touched upon in velocity obstacle. And that was, which is the best strategy? To goal, maximum speed, or structure, or many other strategies that I did not discuss. Which is the best strategy? And the answer to this is that maybe what you could do is apply every strategy for some Tmax times and select the best, or select the one which minimizes the travel time, maximizes the clearance, safety, maximizes the amount that you move towards the goal, reduces the maximum distance from the goal, makes you reach more towards the goal, makes you travel more distance at smaller time, maximizing the speed, all those factors. So for looking at how a robot is behaving and saying is that path good or bad, we've got too many techniques, we've got too many objectives. Path length should be small, travel time should be small, it shouldn't go far away from the goal, it should be closer to the goal. The one that goes more closer to the goal is better. And therefore you can actually do that to find out which strategy is best, I apply all the strategies for Tmax amount of time, assuming that velocity obstacle, it's some arithmetic calculation, and with modern processors, even on robots, it can be done pretty fast. And all the other agents, I assume they move by the same speed. So I do this quick calculation and I calculate my speed. Now the problem is, will a single strategy be the best, or different strategies at different times will be the best. Which means, should I stick with one strategy, or should I create a mixture of strategies, sometimes this strategy, sometimes that strategy? And now it's a more involved problem, because here there were only 8 simulations to do in parallel. We have so many GPUs that can compute in parallel. So parallel simulation, I can give 8 processors this task of one strategy each, and I can get the output. Now the problem is I need to go with all permutation and combinations of strategy possible. For 2 seconds, first strategy, for next 1 second, third strategy, then for half a second, fourth strategy, then for 25 milliseconds, the 8th strategy. Now I've got all permutation and combinations possible, and therefore what I do is I do a graph search. This is my source condition. I apply all the strategies for delta t times, where delta t is a small constant. This is also a resolution. So if delta t is extremely small, you are doing a high resolution search. If delta t is extremely large, you're doing a low resolution search. So that's by strategy 1, that's by strategy 2, that's by strategy, let's say S, last strategy. Then I again do apply all strategies, strategy 1, strategy S, and similarly all others. And it's A star, so it will change as per heuristics, the order of processing of nodes. And whichever leads me to the goal, or in this case, you might not reach to the goal, so applying some heuristic, you'll have to prune. I select the best path up. So this is the velocity obstacle star, where star is an attempt to do a optimal search. And in general, this will be my mantra behind every obstacle, every technique possible. So whenever there will be a reactive technique, and that reactive technique will have some discrete choices to make, I'll always say let's do a graph search over those discrete choices. So here there were some discrete choices being made, which was a strategy. I selected those, I made those as the action function of the A star algorithm. Previously we said just up, down, right, left. Now we're dealing with different options possible. Somebody might say, why not just do it over all possible linear and angular velocity combinations? Yes, you can do that, but those are extremely high number of options. And because those are too many high number of options possible, you know, the branching factor is extremely large. A parent has too many children, and when a parent has too many children, these searches are exponential to the branching factor. So they are exponential on the number of children that a node has, and that will be a bad strategy. Here, I effectively channelize on just maybe 4 or maximum 5 strategies. So I only have one parent producing 4 or maximum 5 children. There also I could do pruning. If many strategies lead to nearly the same velocity vectors, I can always say that, okay, let me prune those strategy, because the velocity they are suggesting is also suggested by another strategy. So I only take as children a diverse set of velocity options possible. So I extremely prune the children, and in a graph search or in a tree search, when your children are extremely small, it is extremely easy. That expansion is extremely small, and that's exactly what happens over here. So practically I only select a few most competent children, I go on expanding them, and what I've done is I have computed the best permutation and combination of strategy at different times. And once I've done that, subjected to this resolution parameter, I can aim to get the best way to avoid all the other obstacles, all the other people, all the other agents, provided that they continue to travel at the same speed, which will not happen, and I will have to adapt and change my decision, of course. There are other few things that I'll just mention. Take the simplest scenario. What the velocity obstacle will do is this agent will in its mind imagine this thing, and it will take this vector, and this agent in its mind, so that's R1, that's R2, that's R1, that's R2, that's R1, that's R2, will take this thing. So initially this agent is actually aiming at this direction, and this agent is aiming at this direction, which is correct. But then immediately afterwards, what happens is that this agent realizes that this agent has actually taken a step aside. So because this moves a little bit here, this moves a little bit here, and this angle turns a little bit here, and similarly this moves. And similarly, because this moves here, and this angle turns a little bit here. So you actually aim at going far to the side and slightly turn your angle, and therefore the trajectory is over here and over here. And this is exactly where the two avoid each other nicely. This is actually something that if you drive a lot, experienced drivers would tell you that if you see a vehicle coming in front, only dip by half the magnitude, because the other half the magnitude, the other vehicle will dip. Your responsibility is only to dip half, the other person's responsibility is dip half, and the responsibilities are equally divided. So we basically say that here, instead of going here, I only aim at half the magnitude, because I know this person will take the other half correction. So this is called as a reciprocal velocity obstacle. And the reciprocal velocity obstacle says that I only apply half the correction, the other half is applied by someone else. We take another interesting situation, and that interesting situation is you are here and there are two people. Now what happens is that you see this one and you aim to go here, but because of this you aim to go here. So you travel here just because you're avoiding R2, but R3 sees you avoiding here and it adjusts its speed over here. But then suddenly you see that, okay, now I'm far away from R2. So now you try to go a little bit over here so as to avoid R3 from here at the correct side. Now R3 sees you going here, so R3 makes a correction of going here. But now you are closer to R2, so you avoid, try going here so as to avoid R2, and R3 sees you going here, it does its velocity obstacle and it again tries to go here. Now you're away from R2 and you again do this thing. Eventually, of course, what will happen is that when R2, R1 and R3 are nearby, this is what's going to happen. So it'll be R2, R1 and R3, and now R3 knows it needs to go here, R1 knows it needs to go here, and R2 knows it needs to go here, which is okay. But there's an oscillation involved here. R1 and causes an oscillation to R3, which is by continuously fluctuating, and that's exactly what happens, to be honest. So you're going ahead and you see somebody walking towards you, both of you are walking casually. Inside your mind it is like, this guy will avoid me from the left, right, left, right, left, right, and you're continuously adjusting for it. Unless and until somebody takes a big avoiding step, you continuously think about it. Left, right, and that's irritating. Similarly, in an intersection, sometimes you're not clear whether you go ahead or the other person goes ahead. You try to go ahead, but then the other person also goes ahead with his own car, and then you stop down that, okay, let the other person go, and the other person also stops down, let this person go, then you accelerate, and then the other person accelerates. So there's a confusion. I go first, you go first, and your decisions keep on oscillating, which is bad. So we've got the hybrid, reciprocal, velocity, obstacle. It says prefer to avoid an agent by the same side as previously unless the other side is now significantly better. So once I say I'll avoid you from the left, I will keep on avoiding you from the left. I will keep on avoiding you from the left unless you make that big move that shows me that you cannot avoid me from the left. So once I decide to avoid you from the left, I will religiously follow that up unless and until you do something that my avoiding on the left is just not possible. So that's the hybrid reciprocal velocity obstacle. There's another technique. So what it says is that R1, R2, R3. Now I know R3 needs to avoid R1 from the right, R3 needs to avoid, R2 needs to avoid, R3 needs to avoid R2 from the left. So if I need to avoid this from the right, so basically I only search for this speeds and I need to avoid this thing from the left, so I only search for speeds within this region. And similarly for all the others, you'll get such half planes about which side you need to avoid, and assuming that the sides of avoidance are into consensus between people, so you get all the half planes and then you use linear programming to select the best speeds for each one of the agents at the correct side. That is the optimal collision reciprocal velocity avoidance. So the optimal reciprocal collision avoidance. So it tries to assign optimal speeds with a guessed side of avoidance between every agent, and it uses linear programming to just select that the best speed. So now, unlike graph search, now we're talking about continuous spaces. So it's a continuous optimization. And in a continuous optimization, you say that, okay, maybe this speeds are better, maybe that speeds are better. So I'll just summarize velocity obstacle before I end this component of the offering. So here basically what did we do was that we started off with the intuition that I should know at what speed I will definitely incur a collision. So that's a small cartoon which shows exactly that. So that's my agent and everything shaded is collision. Then I said that, okay, instead of speed, let me denote the term relative speed. So this light gray is this dark gray is the one which is now the velocity obstacle, and this light gray is the collision cone, where the collision cone is moved by v. I've got the same by multiple obstacles, so I just take a union of all of them. Then I say these are the only ones which are kinematically feasible. So I overlay the kinematic feasibility all over. And if I overlay the kinematic feasibility all over, I see the white which are the ones which I can select. And once I know the white ones which I can select, this is the maximum speed in the direction of goal. This is the one which has the highest safety factors in terms of magnitude, not in terms of angle. And this is the one that anyways has the maximum speed. So instantaneously, I'll select the speed, I'll move for delta t amount of time, and then I'll do the entire calculation once more. And using this, we would see all the agents to happily and nicely avoid each other as they move from their respective sources to their respective goals, avoiding each other in a reactive manner.